Hi, I'm Kevin Fischer from Stanford University, and I'm going to speak to you about our research on particles of light. Up until the discovery of quantum mechanics in the 20th century, the nature of light was hotly debated. A long history of eminent scientists proved light behaved like a wave with interference and diffraction, but Isaac Newton firmly believed that light was a particle. The proof for particle behavior came from understanding radiation from hot objects called black bodies, which required that light be broken up into particles called photons. Further mathematical developments in quantum optics allowed for a refined description of the photon. A photon was discovered to be a single particle of the electromagnetic field. Mathematically, this particle can be described by some beautifully simple shorthand, a dagger, which creates a photon of a given momentum from vacuum. This model had incredible predictive power in shaping our understanding of light. But the specifics of the photon are a bit odd. It extends infinitely over all space, which doesn't seem to capture a realistic particle of light. The development of a field in the 1990s called multi-mode quantum optics resolved this confusion. A complete description of a realistic photon can be built by considering a summation of a large number of those infinite photons. By combining these photons together in the right way, we make something called a wave packet that fully describes a traveling single photon. From this insight, one can imagine that a photon is a distribution of electromagnetic energy, so we draw the photon as a blurry sphere rather than just a billiard ball. This is a mathematically sound and rigorous definition with complete predictive power of how photons interfere with one another. But what produces single photons? One popular source is the quantum two-level system, a system with one ground and one excited state. Beginning with the system in its ground state, then excited by a short pulse, it returns to its ground state roughly by emitting a single photon. But what about more complicated systems? Do they also emit single photons? How are their photons different? Is one more useful than the other in a given application? Here, in our research work, we studied how to characterize emission of an arbitrary system. By examining three simple metrics, we show how to answer the question, how close is the emission to a single photon? 1. The photocount distribution. A source may emit more than one photon at a time, so simply put, does it emit only one photon? 2. The mode profile. How is the energy distributed? The energy could be in a nice sphere, or an oval, or a dumbbell, or actually any shape at all. 3. The first-order optical coherence. Think of this metric as describing how wave-like the photon is, and how it interferes with other photons. In our paper, we developed a theoretical framework for taking an arbitrary quantum system, putting it through a suite of mathematical tools and machinery, and then answering the question of how well does it emit a single photon. In order to make our work accessible, we contributed to an open-source quantum simulation project, the Quantum Toolbox in Python, and provided example code for reproducing all of our simulations from this paper. Thank you again for listening, and I hope this work will be a useful tool in understanding single photon emission.